I will talk about some new results after a long introduction to present all the material which is needed. So let me start from the very beginning. So I will start by two classical models that has been developed in the last 20 years for explaining the evolution of networks. So the first of these models is the so-called Watts-Strogatz model, published in 1998, in which the evolution of the network is considered by taking into account a starting point, which is a circular graph in which the edges are rewired with certain probability. We will going to see later some more details, but the second influential model was developed a year after this one, and by Laszlo Barabasi and Albert. And their idea was to consider the evolution of a network from a small seed of, let's say, a network a la Erdos-Renyi, in which new nodes are attached preferentially according to the degree of the nodes existing in the previous network seed. So in the Watts-Strogatz model, the most interesting thing from the network's perspective was that they were able to capture certain characteristics of real-world networks that combine high transitivity of the relations with a relatively low average path length. So this was a regime observed when the rewiring probability was not too large, and still this network contained a relatively large clustering coefficient, which is measuring the transitivity of the network. Here you have the expression for it, and a relatively small average path length. So what happened when this model is confronted with data from the real world, coming, for instance, from omics, so all the omics technologies like protein-protein interaction networks, metabolomics, gliomics, etc., or technological networks, collaboration networks, etc. What we can see is that for the average transitivity, the real networks behave well, sometimes more or less in the middle of the two extreme cases, the circular graph and the Erdos-Renyi type of graph, but sometimes it is very close to the random graph, and sometimes it's very close to the circular graph. So in many occasions, you can see that there is more similarity between the clustering coefficient of the real networks to one of the two extremes. But if we compare these for the average shortest path, then there is no doubt that the Watts-Strogatz model and at the same time the Erdos-Renyi type of model reproduce very well the average path length for most of the real-world networks. So there are some small pathological cases, but in general, they are very far from the circular graph, and they are much more close to the random type of structure. So in the case of the Barabasi-Albert model, their idea was to try to capture another characteristic of real-world networks, which is basically a skew distribution of the degrees. So the characteristic of real-world networks of having a large number of nodes of relatively low degree and very few nodes of relatively high degree. So in the particular case of the Barabasi-Albert, using the preferential attachment by the model that they define, what you can obtain is that the probability of finding a node of degree k is scaled with a negative power of order 3 of this degree, and here you have the typical log-log scaling for this probability distribution. So what happens if we consider degree distribution in real-world networks? So of course, real-world network is a very wide concept. Let's concentrate into a very narrow window, and in this particular case, I have selected 16 food webs studied by Dune et al. In 2002. They were already observing in a general way that there were several types of degree distribution, but if you do the homework and you try to fix all of these to a different type of statistical distribution, taking into account the goodness of fit, you can see that there is a huge number of different types of distribution, practically none of them is a sort of power law, except one of them, which is a generalized Pareto, which at the end of the day is a power law. So the rest are not. So in general, we have that in many real world situations, we don't have a power law degree distribution. This has given rise to certain debate in the literature. I don't want to enter into the debate, but you can contact the corresponding authors of this paper. Scale-free networks are rare, or the response given by another author, rare and everywhere. So in any case, the point is that not all the networks display this type of degree distribution, not even fat-tail degree distribution, but there is a huge a number of different type of distributions that you can find in real-world networks. But if we go back again to the average shortest path, then we can observe that in the case of the Barabasi-Albert model, the average path length is scaled with the logarithm of the number of nodes divided by the logarithm of the number of nodes. So in many occasions, the real-world networks has average path lengths which are very similar to this scaling of the Barabasi-Albert model with the same number of nodes and edges. In other occasions, they are closer to the one of the Watts-Strogatz model. There are certain kind of pathological cases like this one, which are, for instance, power grids, which are planar graphs, and it is known that they are large worlds by definition. But in general, we can see that both kind of models reproduce a general characteristic of real-world networks of having small average topological distance. So in general, this is also observed by the real-world networks. And in particular, this will imply that all of these networks will be highly efficient in communication process which take place through the shortest path, which are connecting the pairs of nodes. What are the problems here? Well, the problems are that, first of all, in order to navigate through the shortest path of a network, it is necessary to know the whole structure of the network. You have to have a map of the network. And we know that many physical processes, diffusion, advection, synchronization, etc., do not take place through the shortest path. So they go in a more all the different routes at the same time way. And also, even if you have the map and you use very intensively this shortest path, you are going to saturate them. So then there is a sort of contradiction here. Shortest path possibly guarantee shortest routes, but the routes will be saturated, and then there could be possible failures and traffic jams in the system. So in the particular case of the brain that we are interested in this workshop, in this paper in 2013, it was already observed experimentally that the higher degree of connectivity is associated with a nonlinear increase in metabolism. So the highest the degree of the corresponding region in the brain, the highest is the consumption of glucose. So we can figure out immediately that through a hub, through one node of high degree in the network, there will be a lot of shortest path crossing this particular node. So then this implies that navigating the brain using shortest path will represent a high energetic cost for the brain. Although this is apparently very intuitive, there are still authors in the literature that proclaim the important role of shortest path for transmitting information more quickly and reduce brain consumption in the brain. So then it means that if we assume that communication in the brain is used by taking the shortest path, we have to assume the existence of a central controller in our brain with a global knowledge about the network topology that direct the information through the shortest path, connecting pairs of brain regions. So maybe it should be people happy with this idea of the central controller, but from a scientific point of view, it is not sustained. So also in the particular case of the brain networks, Tognoli and Scott Kelso has emphasized very well that the brain betrays an essential communication etiquette. So its parts do not behave in a sequential, one talk at a time manner. So the only possibility that remains here is that the communication between different regions in the brain is by taking into account all the potential routes for navigating from one place to the other. So after this introduction, I will present a quantity that we developed in 2008, which is named the communicability function, that tried to capture all the routes connecting two nodes P and Q in a way that the shorter routes receive more weight than the longer ones. So you can prove analytically that the PQ entry of the K power of the adjacency metric gives you the number of walks of length K starting at the node P and ending at the node Q. So we have selected here the weighting, the inverse of the factorial of the length among the many possibilities, because this converges to a very nice function, which is the exponential of the adjacency metric. Here, this is for now an empirical parameter. And what we have here is just a quantity that takes into account all the potential routes to go from one node P to another node Q in the network, but given more weight to the shorter than to the longer ones. So the shorter walk is absolutely necessarily the shortest path. So if the shortest path between two nodes is 5, this quantity is given more weight to this shortest path than to any other longer route to connect the two nodes. But they are all taken into account in such a way that the communication does not need any central organizer. So if we consider this Taylor series expansion, and we know that, well, the entries of the non-diagonal entries of the adjacency metric represent the walks of length 1. Here, directionality means that goes from P to Q, but the network is undirected, so it can go the same way from Q to P. For the walks of length 2, you have, for instance, between two different nodes, a walk of length 2 is like this. For the case of walk of length 3, you can have walks for pairs of nodes which are separated at the distance 3, like in this case, or for nodes are separated at these two walks length 3 of this. The function can be expressed as a linear combination of the contribution of different subgraphs, or if you want color subgraphs, in which the two corresponding nodes that we are analyzing are colored here. So I have put two colors, and the largest contribution is received if the two nodes are adjacent, but there is a high contribution if the two nodes are just separated by one particular node here, or it takes place in this other type of fragment. So I have truncated here the Taylor series to the power 4 because the combinatorial explosion of these subgraphs grows very quickly. But we are not doing anything computationally in terms of computing these subgraphs. We simply compute the exponential of the adjacency metric, and the non-diagonal entries of these tell us what is the number of all routes of different length from 0 to infinite that connect these two pair of nodes, giving more weight to the shorter than to the longer ones. So at the end of the day, we can have two different types of measures, because I can also take the diagonal entries of the exponential of the adjacency metric. And this accounts for all the walks that start and ends at the same node. We can figure out that we have particles that have a finite and short time of living. So maybe after a walk of length, let's say 3, the particle dies. So then if it go 1, 2, and return to the node 3, it die out in this particular node. So it started and end at the same node. So it accounts in some way how the node V, in this case, retains an item which is flowing through the network. Because if there are many potential routes going from the node V to itself, then a particle can get trapped going around several times around this node and not moving to the node W, which is what we would prefer in order to have a communication between these two nodes. So these other quantify, as I say before, all the routes that move from one, or move an object from one node to the other. So it accounts how much a second node, let's say W, attracts an item that is located at the node V. So if we want a good communication between two nodes, it could be good to think about in the difference between these two quantities, because one quantity is about how difficult it is to move out one particular node, and the other quantity is how easy it is to move to the other node. So then let's go to define a simple quantity here, and I will call this the resistance that a network as a whole offers to an item at node V to go to the node W. And I will take the difference between this attractiveness of the node V and the attractiveness of the node W for the particle at the node V. So then, because we are considering undirected networks, I will simply take the sum of these two quantities for the communication between V and W and from W to V. So if we make the spectral decomposition of the adjacency metric, what we obtain is this expression here. But the good news is that this quantity, which is just a sort of internode resistive function, is a Euclidean distance between the corresponding nodes V and W in the network, which of course is inducing an embedding of the network into certain n-dimensional Euclidean space. And I will show you now that this n-dimensional Euclidean space is a hypersphere. So let me show you one example in order to understand the concept. So unfortunately, we cannot visualize things in more than 3 dimensions. So I will take the particular case of a network with 3 nodes. So in this case, if I have, for instance, these are the 3 corresponding eigenvectors of the adjacency metric, we can rotate these eigenvectors to make this system of coordinates. I am selecting these eigenvectors orthonormalized as usual. So then it means that they are orthogonal, and I have this system of coordinates here. But the important thing here is not the system of coordinates, but these vectors that are created in the following way. So this is the spectral decomposition of the adjacency metric. U is the metric whose columns are the eigenvectors corresponding to the eigenvalues of this adjacency metric. So here I will take the row of this matrix, which is the same as the column of the transpose of this matrix, as a vector which I call phi p, and which is given by the corresponding entries of all the eigenvectors for the node P in this particular case. And the vector xp that you will see is the position vector of the node P in the hypersphere, is given by the exponential of lambda, which is the matrix, the diagonal matrix of eigenvalues, divided by 2, multiplied by this vector. You can generalize this. Indeed, we have done this in this paper in discrete applied mathematics for any matrix function which is positive defined. So any function of the adjacency metric which is positive defined, you can do the same kind of embedding I go to do now. So now we have here the center of coordinates, and I will have the 3 x's here, and there I will place the 3 position vectors that define the place in which the corresponding 3 nodes of my network are located in this particular sphere. So the nodes of this network, or of any network, will be located in the surface of an n-dimensional Euclidean sphere, such that if I take the chord between the 2 nodes here, suppose that there is the sphere over here, the chord, the length of the chord between the 2 corresponding nodes is the communicability distance that we have defined before. The angle between the 2 position vectors is the communicability angle, and the length of the position vectors is given by the self-communicability of the corresponding vertices in the graph. So the communicability matrix is a Grand matrix, so I can take the communicability between any two nodes by taking the inner product of the position vectors of the corresponding nodes that I am interested in. Okay, so because the embedding is in a hypersphere, of course, you can have the radius of this hypersphere, and you can have here a matrix with all the communicability distance between the different pairs of nodes, and this shows that this matrix is circumeuclidean. So a matrix is circumeuclidean if all the non-diagonal entries represents Euclidean distance between the objects, the points, which are represented by this matrix, and the embedding induced by this distance is in a hypersphere. So in a very recent result, and this is really not important for the current presentation, but if you are interested, I have proved that for any circumeuclidean metric, you can remove communicability here, and then for any circumeuclidean distance metric, it is, well, there, if you have any circumeuclidean distance metric, this metric is the metric of effective resistance between the nodes in a weighted graph, which is given by this expression here in terms of the pseudo-inverse of a unique Laplacian, which is associated to this circumeuclidean metric, and the pseudo-inverse is also analytical, and it has this particular formula here. So what we were intuitively calling the resistance of the network to the communication.
Do you hear us? There it is. Yes, oh, back.
Okay. So I was saying that if you want to move from one node to the other, you cannot do like eagle that can fly from one of the top of the mountains to the other. But you are a walker, and then you have to go down by a certain path in the network that is necessarily using the edges that exist in the network. So it means that this distance can give you a certain orientation about the geometry of the graph, but it is useless in order to navigate the network. In reality, what we have to do is to make a geometrization of the graph in such a way that we can obtain a geodetic space in such a way that we can have a path going through the edges of the graph. For doing that, and because I lost a certain time, what we do is simply to assign the communicability distance between every pair of edges, every pair of nodes. So we have here that for every pair of nodes, we have assigned a length which is between 0 and the communicability distance. So if we do this, we can now have a path between two corresponding nodes. So the length of this path is defined by the sum of the distances that are in the edges corresponding to this particular path. So for instance, if we have here two different paths, if I want to calculate the communicability length of this path, I have to take the sum of the communicability distance between these two nodes and these two nodes, and for the other path, the sum of the communicability distance between the three edges which are in the path. If for a particular pair of nodes V and W, we have more than one path, the one having the shortest resistive path is known as the shortest resistive path between the two nodes. So in practice, what we do is that we compute the communicability distance matrix that can be obtained by this formula, and we entry-wise multiply this by the adjacency metric. And then with this weighted adjacency metric, we find the shortest path between the corresponding pairs of nodes. Then it means that these shortest paths are not the topological ones, but are the shortest paths that minimize the communicability between a pair of nodes. So let me show you one example here. And I have drawn this graph like in the brachistochrome, which is an object in which if you fall a ball by using the shortest path, it goes more slowly than if the ball goes by a certain curve that connect these two points. But here what I have is just a simple network. Every node here is colored by blue, and the shortest path between the node P and Q is in green. And I have another path that I have named here P2, which is in red. Now, if I calculate the length of these two paths, for the shortest path, I obtain this value here. And for the path P2, I obtain a value which is shorter than the value that the shortest path receives. So then it means that the shortest communicability path here does not coincide with the shortest path. You can imagine why this happens. So if you are a random navigator in the network, every time that you arrive at this node, you have 1/3 probability of moving to different other nodes. Suppose that you are not returning to the original destination, so original source, so you can move to here, or to here. So maybe you have moved here, you are not returning by these, but then you have 1/2 probability to moving to any of these two. So if you move to here, you are not returning by these, so you can have 1/2 probability of ending at your origin. However, if you do this by using the other path, you always end up at the node Q. So if you do the simulations, what really happens is that every time that you're trying to move randomly through this path, then you can do it in 3 steps if you are lucky, sometimes in 4, sometimes in 5, and so forth, such that the average of all these lengths of path is bigger than if you take the other route. So I have skipped these 2 slides because I want to now make a reflection about what maybe is happening in the Watts-Strogatz and Barabasi-Albert type of models. So when we analyze this microscopically, we can see that we start in the Watts-Strogatz by considering a circular graph. So every node has exactly the same degree, and every node is connected in the same way to other nodes. So for instance, here between V and W, the shortest path is this marked in magenta that goes V, W minus 1, W. Now, what happened in this method is that you select randomly one edge. Let's say that this one, V plus 1, which is here. You remove this and then randomly rewire to a pair of other nodes. Suppose that you have rewired this to the W minus 1 node. What happens here is that you have created here a pseudo hub. You have increased the degree of this node by 1, and at the same time, you have decreased the degree of 2 nodes also by 1. So you have created heterogeneities in the original graph by rewiring one particular edge. So then it means that now there is another path that have emerged here, which is this one in green, which is avoiding the pseudo hub that has been created and is going through the nodes of the shortest or the smallest degree in the network. The same happened in the Barabasi-Albert model, even in a more dramatic way, because what you are doing is increasing every time the degree of the hub. Let's say that at the very beginning in the Erdos range seed, you have a proto-hub here, H, but every time that you add a new node, preferentially this node is connected to H in such a way that it is increasing the degree of this node. Then the shortest path between V and W, if it passes through this hub, it is a particle going in this way has a great chance of getting lost after it arrives at this high degree node. So it happens that other routes are emerging in the graph, like this one in green here, that avoid this hub in order to communicate between the corresponding 2 nodes. So We have then taken some measures for trying to observe if this difference between the shortest path and the path that emerged in this model can be significant or not. So first of all, we have here the resistive length of the shortest path that I will designate by SP here. And by LSRP, between the same pair of nodes, would be the length of the shortest resistive path. Of course, the length of the shortest path, the resistive length of the shortest path is larger or equal than the length of the shortest resistive path. So then it means that for a particle navigating the network, what is important, because the particle don't have a global picture of the network, is what it confronts every time that arrives at one particular node. If it goes by one particular edge, it has to see how resistive this edge is in particular, because it's the only information that it can have. So we can consider that if LSP bar is the mean edge resistive length, and the same for the shortest resistive path, we have this inequality here, which is just derived from this one. And then what we can do is to take an upper bound of this ratio of the mean edge resistive length for the shortest resistive path and the shortest path, given by the topological length of the shortest path and of the shortest resistive path. So then it means that this could be a sort of worst case scenario about how much navigability a particle gain by using the shortest resistive path instead of the shortest path. Well, now we simply modify this to express in terms of a percentage and taking this as average for the whole path that connect pairs of nodes in the network. So let me show you another example with the same graph as before. So here we have that the shortest resistive, the mean resistive path for P1, which is the shortest path, is this value here, and for the path P2 is this one here. So then it means that if we take this ratio, it is telling us that by using the red path, the particle will gain about 30% of energy or effort than if it goes by the green line. So if we do it by taking the easy to compute length of the shortest path, taking into account which one is the shortest resistive one, then what we obtain is an upper bound telling us that the particle will gain more than 25% of effort if it goes through the red than to the green one. So in both evolutionary process, Watts-Strogatz and Barabasi-Albert, what happened is that every time that we rewire the network or add new nodes which are connected, we are changing the landscape of the walks that exist. So it could be that we are enriching the number of walks, or we are decreasing the richness of walks in the network. In order to quantify that, I propose this quantity here, which is, well, it's a sort of probability of finding a walk between the nodes V and W of any length penalized by the factorial of the length, respect to the all weighted walks between every pair of nodes in the network. And then we take the walk richness as the entropy for this particular quantity that we have, and this can be easily bounded after normalization between 0 and 1. So let me show you the results that we have obtained for the case of the Watts-Strogatz model. So here what I have is in red is the entropy or walk richness, and here is the gain that a particle take by using the shortest resistive path instead of the shortest path as average in a Watts-Strogatz model of n nodes. So for different values of the mean degree, what we observe is that the richness of walks increase with the rewiring. So this is very expected because we start from a very peculiar circular graph in which the richness of the walks is very poor. As soon as we are approaching to the random graph, the walk richness is much bigger. But the interesting thing here is that this energy gain in the navigation of the network is non-monotonic. And for every different value of k, you have a minima at exactly one value of probability, which is 0.15. So this is exactly in the regime that Watts and Strogatz claimed that there is the small world type of network. So we have that independently of the size and independently of the degree, we have a sort of universal characteristic here that there is a point in which it is much more favorable to navigate through the shortest resistive path than through the shortest path. And for the Barabasi-Albert, we have exactly the same. Here, instead of probability, we have the mean degree. And then again, as the mean degree increase, there is an increase with saturation of the richness of walks. But there is also a minimum here for the navigability or the increasing navigability or easiness of navigability for this network for independently of the size of the network. So this point that we have here for the Watts-Strogatz of here for the Barabasi-Albert represent a sort of good navigation point. So it's a point in which by navigating by random is even better than navigating through the shortest path. And this could be something that can be used for navigation in the complex networks in the real world. So in closing here, both processes create enough walk richness as for certain bypasses among pairs of nodes emerge. Such bypasses avoid naturally the hubs of the network, allowing items to navigate without effort or saving effort in relation to what it will cost to navigate through the shortest path. So if you compare an Erdos-Rangy type of graph with the same average degree than the Barabasi-Albert type of model, you can immediately see that the heterogeneity is created by the hubs introduced by the preferential attachment significantly drop this energy for navigating in a much better way the network through the shortest resistive path than in the case of the Erdos-Rangy type of graph. So if we do this analysis for real world networks, here I am plotting just the negative of this energy value. So we have that, of course, close to zero, we have networks which are not very efficient for random navigation. So possibly they are designed somehow for using shortest path than shorter resistive path. So this is the case, for instance, of power grids. If you move to the right, you can see that the highest value of negative energy is for the brain functional coactivation network that has a huge difference with the rest of the networks. So meaning that for this type of network, the wiring that the network has guarantee that traveling in a random way, in a diffusive way, is much better than traveling by using the shortest path. So because the shortest resistive path for these networks is much more efficient than the shortest path for traveling between pairs of nodes. So now we wanted, finally, this is the two final slides, we want to compare for the case of the Watts-Strogatz model, if we take one particular real world network, and then if we take the same number of nodes and the same number of edges that this real world network create this circular graph, and then we rewire with probability P from 0 to 1 this network, and then every snapshot of this network is compared to the real one by using certain kind of similarity between the networks. In this particular case, we have selected the similarity of the spectra of both networks, the spectra of the Jessen symmetry of both networks. And then we can find what is the value of P that reproduce, in which the Watts-Strogatz model reproduce better the real world network. So for instance, in the case of this collaboration network in quantum gravity, what happened is that this function is non-monotonic, meaning that the highest similarity, dp is d similarity, so the highest similarity coincide almost exactly with the value of the good navigation point. So then it means that this network is somehow optimized to work at the good navigation point if it were created by a Watts-Strogatz type of random model. But this is not the case for all the networks, of course. So for instance, here the highest similarity is exactly the same as for the good navigation point. Here is a little bit higher for the human brain connectome. For this is a thesaurus network is a little bit higher as well. And there are a few networks in which this function is monotonic, and then the highest similarity between the real world network and the Watts-Strogatz model occurs when the probability is equal to 1, meaning that these networks are much more similar to an Erdős-Rényi type of graph than to a small world type of network. This happened, for instance, for electronic circuits, which has been designed for certain function, and the Internet and Autonomous System also for the year 97 that has been also somehow designed. So in closing, the conclusion here, this is somehow work in progress still, but is that the network is said to be complex if it contains enough word richness as for bypasses emerge as alternative best communication routes between pairs of nodes. Saying very simply, bypasses seems to sustain the complexity of these networks. So thank you very much.